in the earlier lecture we have seen the space of integrands. Okay. We have first considered the space of simple processes, because that is the easiest thing to integrate, that we have defined as L0, okay, in earlier slides, and then we have defined one particular norm, this box norm, and we have shown that under this box norm, okay, the closure of L naught is L star m. Okay, so this result, I mean, we have not proved this, we have just quoted this result. L naught is dense in L star m. In general, when the quadratic variation process of the Martingale of the square integral Martingale is continuous, if one has more regularity property, for example, the quadratic variation process of the Martingale is absolutely continuous, then one can actually have that the closure of L naught is actually L of m. L of m is the space of in right continuous processes. So here this definition is there. This equivalence class of measurable and FT adapted processes. Okay. So we do not even have the right continuity property assumed here. We just have that equivalent classes of measurable and FT adapted processes X, okay, such that this XT norm is finite for all t, so that one can make sense of this norm X. Okay, so that is the space of integrands, and then what we did, we considered the space of we have considered the integration of the process of the integrand. So we have defined, we have started only for first simple process. For simple process, this is the direct definition, that IT of x is just the sum, okay, and this coincides like the Riemann-Stieltjes kind of sense, okay. So this is the most natural way to define integration of a simple process with respect to a square integrable continuous Martingale. Then we have proved that this ITX, okay, this is a Martingale, and then we have talked about a norm of Martingales, okay. So this norm is defined here, and then we showed that, okay, if two processes are indistinguishable, their norm, I mean their difference, norm of the difference is 0, okay. So this is done, and then we have obtained the space of square integrable Martingales with this norm, and we have quoted the result that this space is a complete nonlinear space. So it is the Banach space, and a particular subclass of that is the space of square integrable continuous Martingales. So that is a closed subspace of this space, okay. Here we have seen that this integration of x, where x is a simple process, is a continuous Martingale and square integrable, and we need to prove that the stochastic integration of x with respect to a square integrable Martingale is itself a square integrable Martingale and continuous path, okay. So continuous square integrable Martingale. So for the proof, we first consider s is a time which is less than t. Why do we need to consider two different times? Because to prove Martingale, we need to show that conditional expectation of the process at present t, given the filtration value at s, which is past, is actually the value of the process at past time s. So that we need to do. So we consider s and t, okay, and whenever we fix s and t, we can always find out this t1, t2, tm, okay. So which is actually the jump times of the process x, okay, the simple process, because simple process has discontinuities at some points, okay. In any finite interval, it has only finitely many such discontinuities, okay. So then we consider that tm is the time point where S is between Tm and Tm plus 1. Tn is the time where, which is such that T is between Tn and Tn plus 1. Okay. So, m and n are these two integers. Now, we try to prove the conditional expectation of it of x given fs is actually is of x. Okay. What is it of x? It of x is actually integration from 0 to t of x with respect to m. Okay. So, here what we do is that we rewrite itx in its simple form. So, itx is I mean, from the very definition, it is like a summation I is equal to 0 to n minus 1. Why n minus 1? Because t is between Tn to Tn plus 1. So, here we integrate till the interval Tn minus 1 to Tn. So, these intervals, and then Tn to Tn plus 1 we do not integrate the full on the full interval, but only for Tn to T. Okay. So, 0 to n minus 1, for that we get xi I times mti plus 1 minus mti, okay, plus xi n times, here we write mt minus mtn. Okay. So, this is the value of itx. Okay. Itx is rewritten here, and condition is given with respect to the sigma algebra fs. Now, we rewrite the above expression from, instead of I 0 to n minus 1, I 0 to m minus 1 first, okay, because since s is less than t, so m is not more than n. So, we can write down this way, I is equal to 0 to m minus 1. So, here this, since is finite sum, so expectation can be taken inside of the summation of xi I times the increment of the Martingale mti plus 1 minus mti given fs, plus, so I have here counted only to m minus 1. So, mth one is here. So, xi m times capital M Tm plus 1 minus mtm given fs. Okay. Since expectation is a linear operator, so we can write down these summations this way, and then from m plus 1 to n minus 1. So, this one single summation is broken in these 3 parts, okay, and the last term is as it is. Only thing is that here expectation is taken here. Okay. So, this expectation of the sum is sum of the expectation that we have used. Okay. So, now for this part I is equal to 0 to m minus 1, what we have? We have this all for all I such which is less than or equals to m minus 1, this is at most Tm, but Tm is less than Fs. So, these are all Fs measurable. So, conditional expectation of this random variable given Fs is exactly this random variable itself. Okay. So, since these random variables are Fs measurable. So, here we get exactly this xi I mti plus 1 minus mti, okay, without any conditional expectation. Okay. And now, for this part, when we take conditional expectation of this, we see that, okay, xi m is Fs measurable. So, xi m comes out of the expectation, and expectation of mtm plus 1 given Fs is ms itself due to the property of Martingale. So, we get xi m times ms minus mtm. Okay. So, this is Fs measurable as it is. So, it is as it is. Now, we talk about the last 2 terms. In this last but one term, when I have I is equal to m plus 1 to n minus 1, expectation of xi I times mti plus 1 minus mta given Fs, okay, what we do is that we do another conditioning in between. Okay. So, and we are using the Tower property of expectation. So, what we are doing is that this inside thing, we are writing expectation of xi I mti plus 1 minus mta given fti. Since S is, so what is I here? I is m plus 1 to n minus 1. So, I is at least m plus 1. So, the Ti is Tm plus 1 or more than that, but S is less than Tm plus 1. So, this is a finer sigma algebra than Fs. So, we can use this Tower property. We are writing expectation of xi I mti plus 1 minus mti given fti. okay, and then condition again given Fs. Okay. So, this term is rewritten this way, and then we consider the last term. The last term is expectation of xi n mt minus mtn. So, here also we do again conditioning in the same manner. So, here we condition with respect to ftn. I mean, in this terms xi I is fti measurable. So, I can take xi I outside of this expectation, and then what would be left inside is expectation of mti plus 1 minus mti given fti. But then using the Martingale property of m, conditional expectation of mti plus 1 given fti is mti, and then this subtraction mti is there. So, I am going to get 0 here. For the same reason, I would also get xi n outside of this expectation, and then here I would get 0 here. So, in the next slide I write down this thing. I am summarizing. So, left hand side, the left hand side is expectation, conditional expectation of itx given fs. So, conditional expectation of itx given fs. At right hand side I have already isx. Why is it so? Because this sum what we see is nothing but isx, correct, from the very definition. Okay. And then the other two terms is basically expectation of xi I times 0 given fs and expectation of xi n times 0 given fs, and these are 0. So, I am going to get isx. So, this proves that the stochastic integration of simple process given a square integrable continuous martingale is itself a martingale. Okay. The square integrability part is not yet proved, that we are going to do now. And why is it continuous? The continuous, because that when we integrate the simple process with respect to continuous integrator, at the end we are going to get continuous function itself. Whenever we integrate a step function, okay, so some actually any measurable function you take, okay, which is integrable, and you integrate with respect to a continuous integrator from 0 to t, then the integral as a function of t becomes continuous. Actually, it becomes absolutely continuous. Okay, fine. So, now we get this integration of the simple process is a continuous martingale. We need to just show that it is also square integrable. That means it's that itx minus ixs whole square, this square expectation of this thing is finite. Okay, so conditional expectation of itx minus ix whole square given fs, that we are again writing in earlier way, as for using the definition. So, here when we since this is a difference, so from 0 to that part would be 0. So, I am just going to have s to t part. So, s to t part. So, there I am going to get xi m times mt m plus 1 minus ms with s and onward. Okay. And then I is equal to m plus 1 to n minus 1. Okay. So, if m and n coincide for some reason, then it would be void. Okay. I mean, nothing will be there. Okay. So, xi I times mti plus 1 minus mti plus xi n times mt minus mtn. Okay. So, that is coming from the direct definition of it and is. Okay. So, this is done, and square is written here given fs. Okay. Now, what are we doing is that we are writing down, we are finding out this square. The square, I mean square of sum is not sum of squares, correct, because you are going to get the cross terms also. But here for this case, what you are going to get is that expectation of these cross terms interestingly are like differences of the martingales, the increment of the martingales. Okay, and the increments are disjoint increments. Okay. And then you can again further condition exactly in the I mean similarly as in the last slide, you can again condition in between to take one of the product term outside of that conditional expectation, and then remaining part becomes just the increment of the martingales, and that expectation is 0. So, that would if you do that for each and every such cross term, then you are going to get exactly that, okay, that this is square of this sum is sum of the squares, okay. So xi m square times m t m plus 1 minus m s whole square plus summation I is equal to m plus 1 to n minus 1 xi I square m t I plus 1 minus m t whole square plus xi n square times m t minus m t n whole square, okay. Okay, so after this, now we are going to use the Duesmeyer decomposition result and the very definition of quadratic variation. The definition of quadratic variation is that if you have a martingale, you square it and then look at the Duesmeyer decomposition, where you have a martingale part and the remaining part is the quadratic variation. So now if we do that, then what are we going to get? We are going to get that expectation of this thing, this square of the martingale would be same as expectation of the martingale part in the Duesmeyer decomposition, that would be 0 again, and then expectation of the quadratic variation that you are going to get. So here we are not doing it directly, because you have to first the condition in Tm time, okay, and then you have that martingale square, and then that expectation of square or conditional expectation of this square of this difference is same as expectation of the not this martingale, but the martingale which comes from the Duesmeyer, that would be 0 plus the difference of the quadratic variation. So that appears here. For the same reason, for all of this term, we are going to get exact the difference of the quadratic variation. So Ti plus mti plus 1 minus mti whole square is from there we are going to get the quadratic variation of mti plus 1 minus quadratic variation mti. This is happening because of I mean, I'm not saying that this is equal to this, but I'm saying that, okay, after applying conditional expectation, you would get that this is equal to this thing, okay. So we can get for all these three terms, these three terms. However, now these three terms are showing that if I integrate the indicator, I mean the simple process, which is xi m on the interval Tm to Tm plus 1, etc., and xi I is and it is xi I at Ti to Ti plus 1. If we integrate the square of this process with respect to the quadratic variation process, then these are the increment of the integrator, okay. These are all increment of the integrator, and these are the integrands, okay, so on that intervals. So this is nothing but the integration from s to t of this simple process xi square u dmu given fs, okay. So that is a proof that this conditional expectation of the square of the increment of the integral is expectation of integration of the square of the integrand with respect to the quadratic variation, okay. So let me repeat what it is. It is expectation of the square of the increment of integral, and it is expectation of integral of the square of integrand with respect to here a quadratic variation. Here you had the integration of this is martingale, here it is with respect to the quadratic variation. However, this term is, from our assumptions, this is finite, correct, because what it is just the box norm, correct. So we have considered x to be in the L0, so that means it is assumed that this is finite. So at the end, what we have achieved, we have achieved that, okay, this square, the expectation of the square is finite. So that, or in other words, we have proved that, okay, this stochastic integration is square integrable, okay, its expression is finite. Now for x in L0, that means a simple process, we consider norm of the integration, norm of Ix. So that is we prove here, that is nothing but the box norm of x. It is important to understand that this x is integrands, correct, and Ix is integrals, okay. Ix is a martingale, but X is just an adapted process. Okay, and the box norm. So, these are two different spaces, and these two different norms are defined in I mean separately. Okay. However, of course, I mean the norm, the box norm of X is defined using the martingale itself, the same martingale which appears in the definition of Ix. Okay, so that is the connection. Okay. Now, if we prove that these two norms are same, then what can we achieve? We can say that okay, these two are isometry. Okay, so that I is an isometry. Okay, these two are isometrical. Okay. Okay, so here we start in this manner. So whatever we have obtained here, we put s is equal to 0. Okay, so then we just have itx on the right hand side and left hand side. So left hand side I have just itx whole square, and this will be the 0, and here you have also right hand side just the square norm of x. Okay. So here that thing I have written it more lucidly. So expectation of Ixt, this quadratic variation, is equal to expectation of Itx whole square, and that is equal to, again we take condition with this to f0, and then using the earlier result, this square is nothing but expectation of integration of Ixu square dmu, and that is by definition xt square. Okay, and this term is that Ixt. Okay, so for every n, this is true, n is 1 2 3 integers, and then the definition of norm of Ix is based on the these values for every integer 1 2 up to n. Then we take the minimum that with 1 and divide by 2 to the n and sum over all possible n to get this norm. So if these are matching for each and every t, therefore these two would be equal. So this box this norm is one minimum norm at n, and this is, if you put n is integer, so expectation of mt square. Okay, square root of that. Okay, so and on the other hand, box norm is defined here also. So after this, defining nth one, and then both have the similar formula, so we can see that okay, therefore both are equal. Okay, now for assume that you have one x in L star m, the progressively measurable process. Okay, that is x, and there exists a sequence. We want to prove a sequence xn. I mean, you have already seen, because L naught closer is L star m. So of course we can find out one sequence xn in L naught such that xn converges to x in box norm. Okay, because this L naught is dense in L star m. Okay, before going to this part, let me again clarify that that this part, okay, this this statement is often referred to as Ito's isometry. Okay, Ito's isometry. Mainly Ito's isometry is quoted for a special case when martingale is chosen to be Brownian motion. However, this is I mean grossly stated as Ito's isometry. Okay, so now here xn we choose from the space of simple processes which converges to a given x in the box norm.